This video, we're solving problem 112 from section 11.5 in the Larson and Edwards Calculus with Early Transcendental Functions text. We're asked to find the parametric equations of a line passing through a given point that is parallel to a plane and perpendicular to another line. So we know what we're looking for. We know the answer is supposed to look like this. These are the parametric equations for a line. And x naught, y naught, z naught is a point on the line, and a, b, c, those are the coefficients of t right there. Those are the components of our direction vector. So basically you've got a line that looks like this. It passes through x naught, y naught, z naught, and v either goes this way or that way. I'm going to draw it this way. That's the direction vector, and it has components a, b, and c. So this is what we want. If we had the direction vector and the point that we were passing through, we would just substitute those in and we would be done. But we weren't given all of this directly. We were given one part of this directly. We're told that we want a line that's passing through this point. So we already know that x naught, y naught, z naught could be 2, 0, 7. So we should write that down. That's given to us. So that gives us part of our answer. We're part of the way there. So we can fill in the 2, 0, 7 right here. But we also need a direction vector. Now, they did not tell us the direction vector directly. They gave us other information that will allow us to find the direction vector. So we know this, and we also know that our line is parallel to the plane. Given by the equation x plus y plus z equals 5. And we know that our line is perpendicular to this line, the second line. And that given line has these parametric equations. So they didn't give us a direction vector, but they did give us these two pieces, and this should be enough to allow us to find a direction vector. Now, again, it's harder than it looks. They didn't just give us A, B, and C. We're going to have to do a little bit of calculation, and we're also going to have to think conceptually about what it means for our line to be parallel to a plane and our line to be perpendicular to this given line. So I want to do this second one first because it's a little bit easier to think about. We're told that our line is perpendicular to this line. So basically we've got two lines. Here's our line, and here's the given line. And we know that they're perpendicular to each other. We know our line passes through the point 2, 0, 7. And it has a direction vector v, which is unknown. Now we can draw that vector v anywhere on here. I'm going to draw it at the point of intersection. And we know that this line is perpendicular to this line. Now, I wasn't given the direction vector of this line, but I can infer the direction vector of this line using the parametric equations of the given line. If these two lines are perpendicular to each other, I think we can all see that their direction vectors should be perpendicular to each other as well. Let's say that that's the direction vector. And it's possible that it's going the other way instead. It really doesn't matter. The fact that we're interested in is the fact that they're going to be perpendicular to each other. So the fact that our line is perpendicular to the given line implies that the direction vector of our line is perpendicular to the direction vector of the given line. And anytime you've got two lines that are perpendicular to each other, or excuse me, two lines that are perpendicular to each other, or two vectors that are perpendicular to each other, or usually we use the word orthogonal when we're talking about vectors, we know that their dot product has to be 0. The angle between the two vectors is 90. The dot product is 0. Now the given, or our line has components A, B, and C. We don't know what those are yet. We're trying to find those. We know if we take this and we dot it with the direction vector of this line, we should get 0. Now the direction vector of this second line, the given line, can be found by just reading the coefficients of t here. Remember, the direction vector of a line is shown in the parametric equations as the coefficients of t. So that's your A, that's your B, and that's your C in the direction vector of the given line. So A is 1, B is 1, and C is -1 for that line. So I know that this dot product has to be 0 because these two lines are perpendicular to each other. So we have A times 1 plus B times 1 plus C times -1 must be 0. Now that's still not enough to get us A, B, and C, but it's a start. It's going to get us part of the way there. So that is what this piece of information tells us. It says, if our direction vector has components A, B, and C, we know that no matter what A, B, and C are, A plus B minus C has to be 0. Now the second piece also tells us something about the direction vector of our line. We're told that our line is parallel to the plane x plus y plus z equals 5. Now, I'm not going to draw x plus y plus z equals 5 in three-dimensional space because showing us that first octant portion of that plane really doesn't help us. But we know that our line is parallel to this plane. And there's going to be some perspective where we can look at it and it looks like this. We've got a given plane, x plus y plus z equals 5, and our line is parallel to this plane. So if this is a plane and this is a parallel plane, our line would lie in a parallel plane. Because if our line is parallel to this plane, I mean, it could be going in any direction up here. It doesn't matter what direction it's going in. If it's perpendicular, or excuse me, if it's parallel to this plane, it lies in a parallel plane. Now at this point, we can use the fact that it lies in a parallel plane to tell us something about the parametric equations of the line and an equation that they have to satisfy. Now, there's also another way of looking at this, which is a much simpler way, but I think I want to do the long way first, and then I'll show you how the long way will give us that short way. And then in the future, if you know that a line is parallel to a given plane, you'll be able to use this fact over and over again. So we know that our line lies in a parallel plane, and we know that the equations of all parallel planes to this plane are going to be given by x plus y plus z equals a constant. And if that constant is 5, we're in that plane. If that constant is something other than 5, we're going to be in a parallel plane. So I'm just going to use a capital D for that constant, where D is a constant. Again, just emphasizing it's a constant and it's not a function of t. Now, if our line lies in this plane, then the parametric equations of our line have to satisfy this. And then all the t's have to cancel on this side, and you would just be left with d. D equals d when you're done. So let's write down the parametric equations of the line that we have so far in terms of a, b, and c, and then substitute them into this equation. So far, we know that our parametric equations look like this. We've got x of t equals x naught plus at. Y of t equals y naught plus bt. And z of t equals z naught plus ct. And x naught, y naught, z naught are 2, 0, and 7. Those are the components, or excuse me, the coordinates of that point that we were told is on our line. Now, when we substitute these into the equation of the plane, we'll have this: x of t plus y of t plus z of t is equal to d, where d is a constant. So that means all of the t's over here have to cancel out. So let's substitute in. X of t is 2 plus at. Y of t is 0 plus bt, or just bt. Z of t is 7 plus ct. And that's equal to this constant d. And I'd like to collect like terms in t. So I've got an AT plus BT plus CT, so that's A plus B plus C times T, plus 9 has to equal D. Now, if this D over here is a constant, and this side over here is a constant, well then that constant D must be 9. So actually, now I know that my line lies in the plane x plus y plus z equals 9. And if all of the t's disappear, well, that means that, so that the constant on this side equals the constant on this side, a plus b plus c must be 0. And we know that because we know that our line lies in a parallel plane, and if we're given a plane, all the parallel planes have exactly the same form. You're going to have the same normal vector. You have 1x plus 1y plus 1z equals some constant. The only difference between this plane and all of the planes parallel to it is the constant on that side. So it turns out our constant is 9, and our line lies in the plane x plus y plus z equals 9. And the only way that that can happen is if a plus b plus c equals 0. If a plus b plus c were not equal to 0, there would be a particular value of t that might satisfy this equation, and our line would pass through that plane and it wouldn't be lying entirely in the plane. Okay, so that's one way of looking at it. That's one way to come up with this equation. And we're going to use these two equations to come up with the components of our direction vector. Here's an alternative way. So you've got this plane, and you know that this line lies in a parallel plane. And we know that the line that we're looking for has direction vector v, and v has components a, b, and c. Well, if our line lies in a parallel plane, I think we can see that the normal vector for the given plane is equal to the normal vector for the parallel plane. And if this plane, or excuse me, if this vector is normal to the entire plane, well, then it has to be orthogonal to every vector in this plane. So the normal vector of the plane and the direction vector of the line, they have to be perpendicular to each other. Does that make sense? If this line lies in a parallel plane, in order to lie in that plane, the direction vector of the line and the normal vector of the plane have to be perpendicular. Okay, now if I use that fact and I look at this equation to find the normal vector of the plane, I'll get a relationship involving a, b, and c. Again, it's like this one or like this one. It's actually going to be exactly the same as this. Now remember how we find the normal vector of a plane. Normal vectors were, planes, the equation of a plane was defined in terms of a dot product, the dot product of a normal vector and a general vector in the plane. If the normal vector has components a, b, and c, when you take that dot product, you ended up multiplying x minus x naught, y minus y naught, and z minus z naught by the components of the normal vector a, b, c. So when you get the plane in this form, where it's been completely simplified, and you've got all the x, y's, and z's over here, and all the constants have been moved to the right-hand side, the coefficients of x, y, and z are your a, b, and c. So the normal of this plane has components 1, 1, and 1. So if I take the vector v and I dot it with 1, 1, 1, I get a times 1 plus b times 1 plus c times 1 equals 0, or a plus b plus c equals 0, which is exactly what we got down here. So this is a way that I would go about solving it if I didn't realize this fact by just thinking geometrically. But if you thought about it geometrically, if you said, oh, my line lies in a parallel plane, therefore the normal vector for the plane must be perpendicular to the direction vector of the line, then you could go directly to the fact that v dotted with n must be 0 because the two vectors are orthogonal to each other. Sorry, having trouble speaking. And that means that this dot product is 0. And if that dot product is 0, that means a plus b plus c equals 0. Because that's how we do dot products. We multiply and add, multiply and add, multiply and add, and then we get 0. Okay, now I put these two equations in boxes. It really probably shouldn't be in a box, but this is close. This is going to get us very close to finding the direction vector of this line. Notice we've got two equations with 3 unknowns. If you're thinking to yourself, that's not enough to solve for those unknowns, you're absolutely right. That's okay. Our direction vector is going to have a free parameter. So we've got a plus b plus c equals 0 because our line lies in a plane parallel to x plus y plus z equals 5. And then we also have a plus b minus c equals 0 because our line was perpendicular to a given line. Now I want to simplify this system of two equations with 3 unknowns. One way that I can do that is I can add these two equations together, and then I'll have 2a plus 2b equals 0. Or if I want, I can divide both sides by 2 and I get a plus b equals 2. Or if I want, I can say that b is equal to negative a. Okay. Now this does not tell me what b is or what a is, but I know that whatever b is, or whatever a is, b is the opposite of that. Now, if A and B are opposites of each other, so I replace B with negative A, I'm going to have A plus negative A plus C equals 0, or A plus negative A minus C equals 0. So if B equals negative A, that implies that C would also have to be 0. Now that is enough to get us our direction vector in terms of an arbitrary constant. So A is going to be whatever it is, and B will be negative A, and C will be 0. Now, if you're saying to yourself, my direction vector is not supposed to have this constant in it, why does it have a constant in it? Think about what that constant actually represents. This is a vector that points in the direction, it goes 1 unit in the x direction, or A units in the x direction, negative A units in the y direction, and 0 units in the z direction. If A equals 1, we get the direction vector, 1, negative 1, 0. A vector with those components. Now if A equals 2, I'm just going to make it twice as long. If A equals 3, I'll make it 3 times as long. If A equals negative 3, I'll make it 3 times as long, and I'll make it point in the opposite direction. So the fact that our direction vector has an arbitrary parameter in it is just a consequence of the fact that we can make that direction vector as long as we want. We usually try to keep the components of our direction vector to be small integers, and we usually like that first integer to be positive. So I'm going to choose A equals 1 and let that be my direction vector. Okay, so this is my ABC, and these are the parametric equations of a line. Oops. It's A times T. So all you have to do is replace x naught, y naught, z naught with the coordinates of that point on our line. Now we were given earlier that our line passes through the point 207. So x naught, y naught, z naught is 207, and A, B, C. A, B, and C are given by 1, negative 1, and 0. And normally we wouldn't write ones explicitly like that. So the simplified form is x equals 2 plus t, y equals negative t, and z equals 7. Now again, you could choose any value for A that you want. So if A equaled 2, we'd have 2t, negative 2t, and then no t's. If A was 3, we'd have 3t, negative 3t, and no t's. Or if A was negative 5, we'd have negative 5, and then 5, and then no t's right there. But given my choice of A, these are the parametric equations of this line.